Hi, everyone. Remember that the domain of a function is the set of all legal inputs to the function. I'll often abbreviate the domain of a function f by DOM of f. Now, if the domain is not given to you, we assume that the domain is the implied or mathematically natural domain of f. In particular, we're going to assume that it's the set of all real values of x for which the output is real. We have to keep it real. We have to keep it real. Now, sometimes in a word problem or a geometry problem, we might have other restrictions, like, for example, x has to be non-negative. But for the most part in this chapter, we're talking about the implied mathematically natural domain. So what are the two key sins? When you're dealing with algebraic functions, what are the two key no-nos? What are the two key things that lead to things that are not real, outputs that are not real? If we divide by what number, or if we take what kind of root of what kind of value. The implied domain of an algebraic function. The implied domain is a set of all real numbers, except those that lead to division by zero or taking the even root of a negative value. For example, the square root of -1. I know we define this to be I later on, but again, we're keeping it real. For right now, this is not real. -1 is illegal for the square root function as an input. So for example, if f of x equals 1 over x, or x to the -1, then the implied domain is the set of all real numbers except 0. This is the set in set builder notation, or set difference notation, I should say. The set of all real numbers except 0. So 0 to the -1 is also illegal, because that's the equivalent of dividing by 0. It's like 1 over 0. Likewise, if g of x equals the square root of x, then the implied domain is the set of non-negative real numbers, corresponding to this interval form over here. Now bear in mind, 0 is included in the domain. The square root of 0 is 0, a perfectly good real number. People often forget that 0 is in the domain of the square root function. However, negative numbers like -1 are not, because the results will never be real. Next, let's talk about domains and ranges in general. Remember, the set of legal inputs is the domain, the set of resulting outputs is the range. So for example, for our squaring function, because we're talking about a polynomial function here, the domain of f is assumed to be all real numbers. So if the defining rule is given by a simple polynomial, the assumed domain is R, the set of all real numbers, or this in interval form. Now, what about the range? Now, sometimes the range is difficult to find until you graph the function, but for the squaring function, let's figure it out. So, for example, the square of 3 is 9. So 9 is in the range. But the square of what other number will also be 9? The square of -3 will also be 9. What's the square of 0? The square of 0 is 0. So notice that the squares of the various real numbers here will always yield non-negative results. Non-negative results. We never ever get negative results. We never get negative results. We only get non-negative results. And in fact, every non-negative number is in the range. For example, I claim that 7 is in the range. The square of what number gives me 7. He's a bit uglier, but it is the square root of 7. You can't argue with this. The square of root 7 is 7. So in fact, the range, by this kind of argument, the range is a set of all non-negative real numbers. Here's the range, the set of all y values in the reals such that y is non-negative. Since we associate range with y coordinates, I put y's here, but you can use any letters you want. You can use grandma and grandma. You can use any letters you want as long as you're consistent. Here is the set of non-negative reals in interval form, bracket 0, infinity, parenthesis. Next up, we'll consider the domains of various functions.